Okay, hi everyone. So as usual, we will start around 11:10 and get more people join us. We'll start in about a minute. So any questions before we start? Okay, I would say let's start. As usual, a request for everyone who can turn on your camera, please do so. So we have at least some form of, more live interaction. So guys, please turn on your cameras if you can. Okay. So let's start. I hope you guys can hear me well, right? Okay. So today we're gonna have the week 7, but it's the 6th lecture. So don't get confused. Okay, so far I was teaching you a lot about how to make the circuit to do what we need, right? So we're saying, depending on this task or this problem, I was trying to show you how to make it to do what we need. But we didn't talk a lot about how to make it fast. And that's as important as you can imagine, because everyone in this market competes for speed. We all care not that the phone just execute things properly. We also want to make sure it does it fast, because that changes your experience. So today we're going to spend some time to understanding how we measure the timing on the circuits. It's a little bit different from how you get used to do things in hardware, in software, right? Is it better now? I think it's my internet connection. So please, guys, ping me if it's really unacceptable. I'll switch to mobile phone then. Okay, is it okay now? Okay, sorry about this. Yeah, sometimes my network also lags. Okay, so let's move on. So what we're going to talk today first is their circuit timing. So essentially, as I said, we worried more about the correctness. Now let's think about how to make a circuit fast. And the key concept here that for a lot of you might be new is the latency, right? Is essentially the latency of how quickly information is propagated through the circuit. And it's essentially propagation delay and contamination delay. This is 2 delays. We're gonna briefly get yourself familiar. So for the future, you can think about and argue about how fast your circuit works. Remember, things a little bit different from software, where usually you think about a sequential thread, right? So usually in software, when you think about the code, you think about your program executed instruction by instruction, right? Here, hardware is fundamentally very parallel by design. So a lot of things can happen in parallel, right? So we need to deal with 2 different types of delays because of that. Okay, so when we talk about delay, when we usually want to think about is the interval between 2 50% points. So imagine you had a a transistor that does some, for example, negation. The question is how fast I go from a 50% raise here to the 50% raise here. Okay. So propagation and contamination delay. So what are those? So let me just define both of them formally. So propagation delay is the maximum time from when an input changes until the output or the outputs reach the final value. So okay, is it fine now? Can someone confirm that you can hear me well? It's weird. Okay, sorry about this, guys. Okay, so just for you to understand it conceptually, and please ask me if it's not clear. So there are two types of delays we have to deal with. One is there essentially the best way to think about everything's ready, right? So I might have different paths and I want to make sure that everything is ready by the signal time, and I might have different number of circuits. So this is propagation delay. And contamination delay is the minimum time from when an input changes until any output starts to change its value. So remember, because circuits are so parallel, you might have some parts ready earlier than others. I'm going to show you some examples right now. And that's contamination delay. And it's also important because if something starts to change, but the final value is not there yet, it's a problem for you because you need to measure the change, right? Imagine you have an AND gate and you had two inputs, and one is coming much faster than others. It means that the change already happens, but it's not necessarily exactly the value you want to get out of the circuits. But since it's changing, I need to buffer it somehow, right? I need to know that the change is happening. And the longer it happens, the worse it's for me. So the parallelism is amazing, it's efficient, but if it's very asynchronous, right, and the things arrive completely out of order with a long delay, that might cause you some extra cost. Okay, so let's see at some real examples. It's weird, I don't understand. Is it just the sound or is the video? Okay. So I changed this, the source of their input. Is it better now? Okay, I'll turn on the video for now. Let's see whether it helps, but I'm not sure. I feel like it's the internet in my condo. Okay, can you guys hear me now? And you can see the slides now, right? Okay. Okay, let me repeat again. So given a circuit diagram, calculate the propagation delay and concomitation delay. So what's the difference? So let's think about this gate here, right? This AND gate. As you can see, there's one input coming this way and there's another input coming this way, right? So what the difference is that as soon as this signal reaches, right, that AND gate starts to do something, right? So it means that I need to start to sense the output, and that's contamination delay. But there, essentially, the critical path for the compute is this one, right? Until I get to handle these results, I can't really go into here and compute the final output. So this path is gonna, the critical path, and that's our propagation delay. So we can't really propagate faster. Okay. So that's really the difference between the two. One is the shortest pass, the other one is the longest pass. It's when the pass when everything is ready, essentially. Okay, so so both the propagation and contamination delay of each logic gates are used, and both are important in evaluating different designs. And each of them has different characteristics. For example, if you had an input AND gate, right, then it has 100 picoseconds as an example, for example, for propagation delay, and contamination is faster, 60 picoseconds. What does it mean? It means that that's how long it's really finished everything, and this is how early it starts to generate some output. Can you guys hear me now and see the screen?
Yes.
Yeah, thank you, guys. I believe it's the Wi-Fi is the problem or the router on my desktop. So I will switch to mobile network for now. Okay. Anyway, sorry for the delay. Let's come back. So essentially, there's a propagation and contamination delay for each logic gate. So this is the two parameters, right, that you had to deal with. And each of those, as you can see, is different, right? So AND is a little bit faster, but both has different parameters for contamination, right, and for propagation. And essentially, you can think about one as when the signal starts to change and the output, and as the other one as the value where the results is fully ready, and you can reliably say that the results is out. And it obviously affects things down the line. So let's look and compute propagation delay in this case. So as I said to you before, propagation delay is you're going from here, right? All the way here, all the way here on the, and of course, for propagation delay, I need the worst case scenario, so 100 picoseconds. So let's compute the critical path here. So essentially the path with the largest number of gates, right? Do we have an answer already? So the critical path is the longest path that take from the input to the output to generate the results. Okay, makes sense. So essentially, this is the critical to compute the output. And essentially, the sum of up of all the propagation delay of all the gates will give you the critical path. So here we have one AND gate, one OR gate, and another AND gate. So that's essentially what you need to add up. 100 plus 120 plus 100, 320 picoseconds. You may say, well, that's kind of obvious. I would just do this without any definitions. The problem is it's not enough to look at propagation delay alone, right? Another thing you need to look is contamination delay, right? So contamination delay is different. That's the shortest path. So essentially here you find the short path with the smallest number of gates, and then sum up all the contamination delays of all the gates on this short path. So here, as you can see, the shortest path is this input into the last AND gate. And since contamination delay is here 60, it means that this guy starts to generate some output already at 16 picoseconds. As you can see, there is a huge difference between 320 and 60, right? It means that those two parameters might disagree quite substantially, right? Okay. Question. Is it so the question, is it possible to path with more gates has a smaller delay? Is it possible for path with more gates has smaller delay than so you need to add up the longest latency. So it's not just the total number of circuits, it's actually the total latency that matters, right? So it might be the case you might have a few small gates, but they might be very heavy gates, and then they might dominate it, yes. In other questions, will there be times when the physical length of the wire need to be considered? Yes, but we're not going to go into that in this course. As you can imagine, the wires doesn't have an infinite speed. So the fastest you can go is the speed of light, right? So you're not going to get faster than that. So the longer the wires there, that cause the latency. I'm going to briefly mention that when we're going to talk about memory, like DRAM and other stuff. So it does play a role, but not into the small circuits. So here is everything is very fast. And another question is, why does OR contaminate sooner but complete slower? Very great question. It really depends on the circuit design. And remember, the numbers I gave here is one more for example, but it's possible that essentially that the numbers I use would be more or less realistic. But again, remember, this is just an example for the course. That's not a real numbers. Those real numbers are going to look different. They differ by technology, by the process that the company uses right now, and by the frequency. So all of that is a parameter. Okay, did I answer all the questions? To everyone who asked the questions? Okay, so let's move on. Okay, so another thing we're going to use is a tri-state buffer. So as you can see here, we had an input A, and we had an activation signal, right? So that allows us either to let the signal go through or not to go through, right? It's a very easy tri-state buffer. Okay, and that's a couple of examples of different circuits that we can design. And we're gonna now compare them in terms of how well they would, propagate the signal and how well they're gonna contaminate the signal. So, so this is two different designs for 4-to-1 maxes, right? So essentially, this is on the left-hand side is one correct design. This is another correct design. And this is this tri-state buffers that I told you before, right? So that just allows, either to make signals through or doesn't make it through, depending on the input, right? So let's compare which one is better, if we really can argue on which one is better or not. So that's a good example of whether we understand what we learned so far. So this is a table on the right, just reminds you what are the propagation delays of each single gate. And remember that's example ones, right? So NOT is 30 and to input AND is 60 and so on. So let's look at this one on the left-hand side first. So there are two propagation delays here. Remember, they had input D with the bits, and there are also S as an input. So there are two different propagation delays, one from D to Y and another from S to Y. So let's first look at the D to Y. So what is the propagation delay? Well, the propagation delay here is relatively straightforward. We had a tri-state delay that is 50. You see the line in this table, which is 50. And to go from here to here, this is one, this is another one. So really just 100 picoseconds. Let's look at S to Y propagation delay. So what's going to happen here? So essentially, it consists of two stages. It needs to run the enabler, so enable signal, and the tri-state enabler is a little bit faster than going through this input. Again, why is that? It's by the, the designers that actually tape out the chip, just give us these parameters, right? So it's based on the design out of transistors. They happen to generate this circuit that has these propagation delays, and we're just getting a table of those. So S to Y is going to be enabling from here and another propagation here. So it's going to be essentially 35 plus 50, 85. So this is something to remember. We get 100 for propagation delay and 85 from S to Y for the first design. Let's look at the second design and see whether it's better or not. Well, first again, let's look at D to Y propagation delay. So first of all is that propagation delay here, as you can see, is just a latency of, 1 AND, right? So essentially 1 AND, is of one tri-state, right? And S to Y, so sorry, let me explain this better. I rushed a little bit. So as you can see, signal to get from D, so D input is here, right? That's a design. So the D inputs go just through the tri-state buffer one, right? Right here. So it's just 50. Is this clear to everyone? So the D input is just the delay is 50. But for S, we have to go through 3 gates. We need to go from NOT, we need to go from AND with 2 inputs, and we need to get it through tri-state enabling because we need to go through here. So essentially, the propagation delay from S is going to be 125, right? So that's the difference between the two designs. First one gave us, I think, 185, and this one gave us 50 and 125. So it's not an easy thing to say which one is better. It really depends. So essentially, this is what we get at the end. We get one circuit with this propagation delay and another circuit with this propagation delay. So question to you, how are you going to decide? So someone asked a question, where is EN? Muhammad, can you explain your question better? So what was your question about? The enabler signal for tri-state coming from the top. This is the enabling signal, right? It's coming from the top. It's either connect or disconnect. Okay, so the real answer here, I guess I challenge you. So there's no like simple answer here. The question is whether we know whether the inputs arrive at the same time or not, and they arrive differently. So the question if D and S arrive at the same time. If they arrive at the same time, then we prefer the first circuit, right? Because then the maximum latency, right, propagation latency is 100. But it's totally possible that things might not arrive. So S might arrive early, right? It might be available as an enabling signal much earlier than the output, right? So in this case, if D arrives early, we might prefer sometimes the second circuit, depending how early it arrives. It's totally possible because the enabling signals might be ready early, but the circuit for the max is when you wait for input, you might need to wait for inputs longer because it comes from another circuit. So the answer is it really depends. So there can be cases then one is better, there can say that another, you need to know what arrives early, right? So this is why the problem of optimizing circuits is a very non-trivial problem in general. If S arrives early, it's a different story again, right? Okay, so again, delays, the lower, the higher, the better. So that's the question that we ask here. So for propagation delay, it's usually upper bound. So we usually try to, get the max of it. So to make sure that things are propagated fast enough. Shorter propagation means getting answers better. So usually we try to reduce the propagation delay because it's maxed out. So how we can make the propagation delay shorter? We try to cut the critical path. So try to make sure we had fewer circuits and the cheapest circuits, the ones that doesn't increase the latency a lot. And contamination delay is the other way around. It's usually lower bounded. So we want to reliably sample the value before it's changed. So because of that, we can add buffers, right? So that's one of the ways to deal with this problem, okay? Okay, so essentially the best way to think about it is like animation. Like as you make images in transitions and where the different states are, this is pretty much what you get. Okay, any questions before we go to the major topic of today's lecture? But I hope you get a sense on what it is to analyze the circuits and how is it a non-trivial problem to solve. So the buffer is something that just copies the value, and that value is just propagated with some delay, but you can make sure it's not lost. So the buffer is like similar to programming language, is something where you temporarily store the value. So someone asked, can you explain S and D again and when something comes early? So let me go to this slide again. So essentially, when we decide about two circuits, if we would assume that both inputs D and S arrive at the same time, then the circuit one has the smaller total latency because that's where all the results will be ready. Here, circuit two is delayed by S to Y path. But if it happens that S arrives early, right, and D arrives, for example, later, then this latency here might not be as critical because it would start to compute early than the rest. So depending on what input arrives early, right, then it's totally possible that you might start computing early. Yeah, so it's try-input buffer is just a transistor of some sort. Yes, we're just looking at its logical implementation right now, right? But it is just a transistor, yeah. And every transistor has latency, right? So what if D comes early? So if D comes early, right, that means I will start to compute along this path early, right? So then that means the advantage of this guy versus this guy is less of important because you anyway delay by S to Y. So these guys would be a preference for sure. Okay, what I'm trying to show is not how to solve all the problems. I'm showing that the problems are quite non-trivial, right? You might have different optimal paths depend on each circuit, right? And it means that sometimes one solution is better, sometimes other. It's not like one design is always better than the other design. Okay. So before your goal was just to make it to work. We didn't even think what would be faster. Okay, so any other questions? So let's, if there are no questions, let's move on to their, to the second big part of their talk today, and we will continue this big topic for a while now, which is processor components, right? And we're trying to get you a feeling what it really means to build a real processor. So far, we learned how to build combinatorial circuits, how to build devices, sequential circuits, finite state machines. So we learned quite a bit, but we still didn't meet anything real, a big thing that can compute. Yeah. So David asked, what if they arrive at the same time? We choose the first. Yes, we would choose the first. Okay, hope I answered your question. Okay. So essentially, at the very end, we're going to get something sophisticated like that. And remember, this is a very primitive diagram of the CPU. It's actually much more complicated than that, but already looks very complicated. Like if I would just give you this diagram, it wouldn't be easy to guess what's going on. But in a few lectures, you would actually understand what's going on here. Like all the pieces of it will be covered. So this is where we're going. But let's look at the high level. So at the high level, things are a little bit simpler. And this is the power of abstraction. Remember, we're trying to abstract things we don't need to understand right now. So processor is going to build out of 3 big units. There is arithmetic unit, something we're going to talk a lot today. Then there is storage unit and controller unit. All these units are going to be built of the primitives we already learned, but you're going to see how those primitives now are helping us, right? So today we're going to mostly talk about arithmetic unit and the data path. And next lecture, we're going to talk about storage and control. Okay, so what's the fundamental difference between data path and control? Data path is the place where the computation happens. This is where you really compute, where you read the data, where you do your add or multiply or subtraction. So this is usually done as a diagram of a real wired connections, right? That's what the data path is. The control unit has a very different purpose. The control unit orchestrates the actions that take place in the data path. So it tells you, take this and do this instruction, take these parameters. So one is the person who actually does the job, the other one is kind of the manager, right? The control unit is a big finite state machine that instructs the data path to perform all appropriate actions. Okay. This is some, example of how the data path can look like without going into details. Just wait for the real examples. So let's look at a real example of something you want to compute and how data flow is different from a control flow. So here, we're trying to calculate x squared plus 2x. And we assume that you have access to a value from an external source. Let's not think about where it's coming. Eventually, it will be coming from registers or memory, but let's not worry about that for now. How would you calculate that value using the components you had so far? And the components needed is the LU, so you can assume you can add, subtract, multiply values. You can have multiplexers, remember we learned about them, to determine what inputs should be used for LU. And we can use registers, so the places where I can temporarily store the values. And we already practice of building most of those things except of maybe LU, and we're going to cover LU a lot. So this is a schematic here of what we do here. And it looks a little bit complicated, but I'll show you on the next slide how that really works. So essentially, there is several maxes where you can select either first parameters or different parameters. And this is a LU instruction, and that LU instruction can take 2 parameters, and it can do different operations. It can do add, it can do multiply, right? So what it does at each point of time depends on which parameter we're going to give it here. And this is the data flow, and that would do everything. So the thing that might look confusing here is like how this thing can do everything for us. Well, because it's smart, that data flow covers all possible cases here. So let's do the calculation using here. So step for x squared plus 2x, that's something we want to compute. First, we load value x into register A and register B, right here, like we do the load. And then we multiply array and array B. How we can need to multiply it? Well, first of all, we need to make sure that this LU here gets the right parameters. So you want selection logic here, pass the right value here and the right value here, and then you do multiplication, right? And then you can store result in array. So like essentially we have this path here that would allow us to load value again, because this is just a temporary parameter that I want to get. It's not the full output. After that, I want to add x to array. So, right, so that's, you see, that would allow us to store x plus x, and then add x to array again, right? So this is one way to do it. You do x and you do another x. That's not the only way to do it, but that's one way to do it. So you add up x squared plus x and then plus another x. And then the output would be x squared plus 2x. So this is the data flow that covers the whole transition multiple times. The way to make it to work is we need to orchestrate it. And that's orchestrated through the control signals. So in this graph, I was showing you just the data flow, what it does, what it passes, but it's orchestrated by the control logic. So the control logic, for example, says, select x to a to 0, load to 1, load to, and LU op to just a. So it means like you just don't really do anything here, right? So essentially that does the load, right? Then when you do multiply, right? So what you do, you want both select logic, select the parameter from array and RB, right? So that select logic is going to pass this and this. And I want LU being a multiply. And I want the load to be now so active, so I can load array with the right value. So what's going to happen, I'm going to get x, another x, multiply them, get x squared, and then load it. And so on and so forth. So all the steps here are encoded by some control signals. So you see how the job is distributed, right? This data flow just follow the path of computation. These guys tells the data flow what to do, okay? So we need to build a data flow for LU, right? For generic LU, what's going to spend the next hour. And after that, we're going to talk about the control flow logic that exactly manipulates it. We're going to keep talking about what it needs to do already, but eventually going to formally define it. Okay. So who's these signals is the control unit. So the control unit is essentially a giant finite state machines synchronized with some system-wide signals such as clock, and it outputs the data path control flow signals. It controls all the maxes here. It controls the LU operations. It controls what to load and what not to load. Yeah. So Sam is asking whether that's what it's doing as square plus x, and yes, this is what it's doing. There is another alternative would be to do x squared, then store 2x, and then add up that results, but it would be, apparently in this case, it would be worse, right? Okay. So some architectures also output it on signal. Sam, did I answer your question? So this question is essentially doing what I described, yeah. And that's not the only way, but this is an easy way to do it with just one data flow, right? And we don't need extra intermediate values to store. Okay, some architectures also output a done signal when the computation is complete. So this is another output that we don't show in this data path. Okay. Okay, so this is essentially the schematic of data path plus control. So remember, this is data path logic with LU registers and maxes, and there is a control logic here. This is big finite state machines that get a go signal because a clock that selects all of that. This is schematic way of the process operation. Any questions so far? It's still relatively high level. We're going to go deeper right now, but it's fundamentally what's happened, right? There is a reason why I force you to learn about finite state machines and registers and maxes. Those are the building blocks of a real processor. Okay, any questions? Okay, so these signals are optional for whenever the operation starts and stops. Okay. Okay, this was a preparation to build something called a microprocessor. So microprocessors are essentially our ultimate goal. It's a digital device that processes input, can store values, produces output according to a set of onboard instructions, right? And it can perform, a lot of different computations using the basic primitive operations we already know how to do. Okay, this is how it looks like in the most primitive version I can imagine. And just to remind you, this is what we need to build at high level. And the first thing we're going to focus today is the arithmetic thing, right? Arithmetic logic. Okay, so as I said, that's what it exists from. And today we're mostly going to be focused on the arithmetic thing, the arithmetic logic unit. Okay. So this is where we are in this like big diagram, right? So we are going to cover the arithmetic logic units. After that, we already had finite state machines. We're going to be able to come here and finish the processes. We're going to get memory, registers, and control logic. Then we're going to cover that. And all of that is going to be fitted with an assembly language at the end. Okay, so what is arithmetic unit, logic unit should do? Well, the first microprocessor process were calculators, and they were able to do adders and subtractions. So our adder should be the minimally do something similar, right? This is a part of a larger structure called the arithmetic logic unit. Our unit is going to be do more than just adders and subtractors. I'll show you. And this larger structure is responsible for processing all data values in a basic CPU. So essentially, in a standard CPU, if we don't go to more complicated circuits, this is pretty much at the core of the compute. This is the guy that does all the heavy work. Okay. So what it has as an input? LU performs arithmetic operations. So it needs to be able to take those inputs, like say inputs A and B as two parameters for all the binary operations. Sometimes it just needs one. It means that then the other one will be disabled. So A and B are operands. Then there are select bits indicate which operation to perform. Remember, I don't want to build a thing that just does add. I just want to have one unit that can do a lot of interesting stuff at the same time, but I need to control it. So I need a select bits that would tell me which operation to use and in which mode to run. And you're going to see we're going to have several different modes of operation for these LU units. And the two major ones are arithmetic and logic mode. And the carry bit, Cin, is used in operations such as incrementing an input value or the overall result. So there are some, carryover inputs that might be useful here. And there are outputs as well, right? So the outputs of the circuits are, obviously there is the output itself, right? The result of the output, but there are a lot of other things. So that are like a side effect of the operation. There's overflow condition. So the result of the operation could not be stored in n bits of G, meaning the result is not really correct. So remember all these overflows that we've seen before, that what really affects things, and it needs to be reflected in this overflow bit. So the higher level of the hierarchy can sample that. Then there is also a carry out bit, right? So something that you might want to pass over if you do some, complicated extra bits that needs to be passed through. Then there is a negative indicator bit, whether the value is negative or not. And there's zero condition indicator as well. So all these bits are useful. You're going to see why later when you learn about assembly, but this is just the bits that are returned on top of the regular output. I know it's a little bit schematic, but I want to understand what we're building, what the requirements are. Okay, this was just what we call an API, right? Essentially, the protocol on how the unit operates. But what is inside? What is the A of LU? So it's called arithmetic logical unit, right? So we focus on A part first. On the A part, we want to understand how LU does all the operations, and we're going to focus on their arithmetic part. So fundamentally, this size is really built of an adder and subtractor, very similar to these old calculators, right? It's really not that much different than they are, right? Okay, so, and luckily, we already spent substantial time in this course building an adder, right? So this is essentially what we're going to have here. We're going to have, an adder of a certain precision, and we're going to use it to build the A part of the LU. Okay. So again, we don't need to reinvent the wheel. We already know how to build adders efficiently, and we can also use the same adders for subtractions, right? That's what we spent the whole, class on. So that adder, maybe in a more efficient form, will be part of this LU. So LU block diagram is essentially, in addition to the inputs and outputs, the circuits had, some extra bits, right? Outputs different conditions, but obviously you need data input. Input can have up to n bits. So you, if you had like 32-bit precision, that's going to be 32 bits here, 32 bits here, right? This is n bit LU, right? Whenever someone says that your machine is 64-bit or 32-bit, that's what it really means. And then there's all this, obviously there's an output that's the same precision, 32-bit, and then there's all this side flags, carry output, overflow, negative, zero indicators. It's very helpful. Inputs specify the operations to perform, similar to sub. So like I need to tell the LU, the A part of LU, which operation to do. So there can be an operation and mode selection bits that will be passed in these extra bits here on the side. And there's also carry input that's possible. Okay. So what are those arithmetic components here? In addition to addition and subtraction, many more operations can be performed by manipulating what is added to input B, as shown in the diagram above. And essentially, I'll show you how I can manipulate the bits to get a lot of really cool operations. But that's the schematics of it, right? We had this big unit that's supposed to do X plus Y plus C input, right? But I had a control over what comes here, right? So it allows me to manipulate on what's done. So let's look how I'm going to do it. So if the input logic circuit on the left sends B straight through, then there's nothing interesting happens, right? It's just A plus B. But what if B is replaced with all ones instead? Then all ones means -1. Remember the complementary definitions that we learned, the 2's complement. So essentially all ones means -1. So result of an addition operation would be actually A -1. So by manipulating the B, I can not only get A plus B, I can get A -1. Anyone would say why A -1 is useful as a separate instruction? Anyone? Are you guys still with me? Yes, counters. Yeah, so the counters that does -1 or +1, that would be good. So you can get an extra counter like that, and you can make it a bit faster than the regular A plus B. Okay, so what if B was replaced by, B naught? Well, if you replace B with the 2's complement, since the negation of it, the results of addition operation would be A minus B minus 1. And what if B was replaced by all zeros? Then it will be just G equals A. It doesn't look extremely interesting, but you will see later on that it's useful actually. And instead of a sub signal, the operation you want, you can signal other, other features, right, other than the sub. So essentially, this is what we can get using the state tables of S, using that logic for addition. So if all their control flow bits, the side bits are zeros, then we just get a transfer. If you get 0, 1, then its second input is just the value B, and then you get addition. If you get 1, 0, you get subtraction -1. And if you had both ones, then you can get a decrement, A -1. So you can see by just manipulating a few bits and how to interpret things, we can quite easily get a lot of different instructions. It's a good start, but something is still missing. So how about the carry bits? Remember, there's also a carry bit that we had. So depending on the carry bit set, we can get actually more. So if the carry bit is set to 1, based on the values of the select bits, we can do even more, right? We can perform more basic operations. So if we carry it as 1, carry in as 1, remember it will be added as well. So in our added circuit, so then if this is two as zeros, but carry in as 1, not 0 as we treated here, instead of being transfer, that becomes increment. Here, we're seeing we can get a plus b plus 1. Here, we can get a plus, minus b plus 1, and then get another transfer here. So overall, we can get a few more instructions pretty much for free by just manipulating a few bits. Okay. And I want to add, let's logically stop here before we move into other big parts. So let's meet in 10 minutes, and hopefully I can figure out my network before that. Thank you, guys. See you in 10 minutes. Okay, for people who are here, can you hear me well? I'm just testing, because I run all the testing tools I can. It shows that the internet connection is fine, so I don't see, yeah. Just so many things can go wrong. It can be, you know, Windows update on my desktop. It can be internet provider. So I run several different testing tools for stability of the traffic. It seems to be okay now, so I don't know. If it's gonna lag again, please let me know. Oh, I had much more sophisticated tools that sends a lot of packages and track both incoming and, you know, download and upload traffic for 10 minutes. So to see, yeah, so I run the tool, like it's for 10 minutes, there's not a single packet was lost. So it's hard to say what was happening, but it was happening before this meeting as well, just not that terrible. Anyway, so I'm using this network for now. It doesn't seem that that's a wireless driver on my machine, because when I switched to a mobile network and using Wi-Fi on my desktop from the phone, it was working fine and you can hear me. But sounds like it's probably provider of the internet. Is it guild? Yeah. And so let me answer. There is a question. Why we do not have an input logic for A2? Why not for both? Good questions. Any potential answers? Like I'm just curious who thinks what. Like, why wouldn't we do the same thing as we do with B for A? Any theories? Okay, so first of all, I don't know the 100% sure answer, but like I'm kind of confident the reason why this happens is that when designers look at the options to add extra signals to A similar to B, they don't see a lot of advantages. Why? Because, you know, A plus B is equal B plus A, right? So really, you would need to add some extra control flow logic, but everything you can achieve can be achieved by just reordering the parameters. And by reordering simultaneously certain bits in A and B, we didn't get any new interesting instructions. So there was nothing you can gain interesting. So there was no much gain and extra overhead. So they decided not to go with it. So pretty much everything you can get, you get. When you're going to learn assembly language, you're going to see a lot of tricks like that when some instructions are not symmetric. So for example, you might have one instruction in which one parameter can be of different size, and another one has a restricted size. And when you say why it's only the second is restricted, because otherwise you can always reorder things for associative instructions and commutative. Make sense, David? Guys, can you hear me well? Can someone, you know, highlight that they got my response? Yeah, okay, thanks. And please try to enable your videos again. I really appreciate that. I know that there was some connection issues, but if you can turn on your camera, then that would help me a lot. Okay, let's move on. So we so far work on LU part, like a part of the LU, and we get some progress, right? You notice that we were able to get a few different instructions working. So how about the L part, the logic part? So we also want a circuit that can perform logical operations, right? In addition to arithmetic ones. But before we go into that, let me ask a high-level questions from just, you know, first principles. Why do you think people fit so many things into arithmetic and logical units? Why not have add, subtractor, logical operations, everything separate, and then somehow control it. Like, why would the designers put everything into one unit? Anyone wants to try to answer? Just what's your intuition about it? Like, why is it all in one unit? So several answers here, and they all cover the right things. Let me go one by one. I like that you guys thinking, because there's no like correct answers on the slides for that. It's just about thinking. So Sam said the circuits that do different operations are similar, right? And yes, there is a very helpful. And as Juan, sorry if I mispronounce your name, says you reuse circuits. Yes, first of all, we reuse some circuits, and then that's helpful from the designer perspective, but it's also very helpful from designer perspective. It keeps everything simple. As humans, we don't like to design things that has too many dependencies on complicated wiring between them, even logical wiring. So it's nicer to think that this is one big box, is going to do all compute for me needed, right? And I just feed it with the right inputs, and it does do all the magic, and I don't need to worry about it. Rather than designing or an AND here and adder here and subtractor here. So it's a combination of this factor that leads that pretty much any design, you're going to have LU like that. There might be some differences you're going to see later on in your career when you're going to learn more about hardware. You're going to see some cases where it's slightly different, but all general purpose compute units look the same way. And then George said cheaper, which is part of reusing the circuits, right? Yeah. Okay. I hope everyone's clear about that part, right? That's helpful. Okay, so it's not like that's artificially made up for the class, right? There's a big intuition in designers, and people are designing these machines from like mid-40s, right? Before even transistors were invented, they were already logically trying to build things this way. Okay, so the L part. So we did adders, but we obviously want to be able to do logical operations. Why logical operations are so important? Like we definitely do a lot of adds, multiplications, subtractors, but why do logical operations are so important? Like you guys all get experience with programming, you should be able to answer this question. So why do we need logical operations? Why they're so important? Any theories? I try to get you a little bit more involved, right? So I'm asking all these interesting questions. Yes, Sam has answered the questions correctly. That's the major reason. There are some other reasons, and they're the same. Yeah, if statements, conditions, right? Your code that has no if statements and no loops, right? It's quite boring, right? There's not that much you can do with it, right? So you really need that, and all these conditions are built of logical operators, right? So you need logical statements. And there are other cases that you're not that familiar, but when you're going to learn about, say, databases, you're going to learn that there is a need in some cases to do massive logical operations on some predicates. Some algorithms require by design a lot of logical operations. For example, I work at Microsoft Research for several years, and there we obviously, as researchers, try to accelerate the Bing search engine. And I don't expect the Google search would be much different. So those at the very bottom of their compute engine for the search, it actually does tons of logical operations that is store all your search query and all the websites in a certain format that is really just zeros and ones based on what information is stored or not. And the way to find that something maps to these web pages is by doing a lot of and ors. So at the very bottom, it's like everything that's Bing's core compute engine is doing is a lot of and ors, right? So logical operation is indeed important in many use cases. Okay, so hopefully I can rinse it. It's useful. So we want to do essentially logical operations, not just arithmetic. So how do we know which operations to perform? Well, we're well occupied to answer these questions. We know about maxes, right? So we don't have to do the selection. So we just add extra selection bits, and that would tell us which of the logical operations to use in different cases. And if S2 bit is 1, then magic happens, the logic circuit is activated. So we had a control bits that would tell me whether to use my LU as A or as L, right? So that S2 bit is the one that flips the bit. And as someone, I think a couple of you mentioned shared circuits. So when we're going to build things, you're going to realize that mathematically sometimes something that does a logical operations can be used as an arithmetic operations. So you don't want to have separate transistors to do identical manipulation on the bits. You just tell, oh, this time I interpret this as AND, and in another case, I interpret it as subtractions or something like that, right? So this is the trick we use. So multiplexers is used to determine which block logical arithmetic goes to the output. So it can schematically work like that. There is no sharing here, but in reality, there might be optimizations, right? But essentially, so in simple form, you just tell us, look here and use this output, or you take here and S2 manipulates on which output to take, right? So which one to take. As you can imagine, this scheme is not optimized yet, but it just schematically tells you what to do. What is not optimized here, by the way? Like what is, like if you look at this design, if you really, had this engineer mentality, what makes you unhappy about seeing this diagram? Like my background is CS, but I like to treat myself as an engineer when it comes to computer architecture. So there is something on this diagram, that's how they normally teach B58, that they show you, but there's something that should bother you here. Some said marks separate. Well, that's not the major issue. So no shared circuit. I said this is just simplification, but in general, think about it. So what's going to happen? Like, remember, circuits operate in parallel, right? What's going to happen is that no matter whether you do logical or not, you're doing both things, right? Even if you just look at this diagram, there's no like a logic say, don't do this, just do that, right? They do both things and then select the output, right? So there are pros and cons for that. The bigger negative side, you're going to burn energy, right? So you're going to burn energy doing something and you're not going to use the output, right? The good thing about it is latency. And if you can handle the latency aspect, then probably you're not going to do it this way. The latency means you're not doing some smart logic here, because that would increase the critical path. You do everything in parallel and takes what it's needed. And that's wasteful, obviously. And if your power is a big concern, that's not great. Okay, I hope everyone got it. Okay, so we now get into a little bit more complicated topic that's called multiplication. Today, I'm going to explain you how you're going to do multiplication. I'm not going to cover division and other more complicated instructions. In fact, things like divisions and floating point arithmetic, if you're old enough like I am, or if you go to a computer museum and look at the early x86 machines, you would actually notice they were not capable of doing some of this complicated logic. You would need to buy not just, before Pentiums, there was like 86, 286, 386. So I work on all these machines as a child. So those machines, you might not be able to do sophisticated logic without buying a separate coprocessor that would do that logic for you. So right now it's unimaginable, like your CPU is going to do everything. So this is because those instructions are getting more and more complicated. And so we're going to cover multiplication that all support, but say division or floating point arithmetic is also supported. I'm not going to cover this in this class. So remember that would be done as well and would make a chip more complicated. Okay, multiplication. So I'm going to cover the basics ideas behind multiplications. And there is a Booth algorithm that, depending on the instructor, sometimes they go into very details of that, sometimes they don't. I will gonna cover it generically today. I don't want to throw all the details of the algorithm on you. And if we have some time in the tutorial, I'm gonna cover that a little bit more. But essentially the idea is we get add and subtractor and logic. But we occasionally want to do multiplications and divisions. And as you can imagine, multiplication is more complex operations than addition, right? and logical operations. So we need a way to implement multiplication using existing circuits. We don't want to do it from scratch. So there are three major ways to do it, and we're going to cover each of them one by one. And if I'm too fast, please slow me down and ask questions. Okay. So multiplier circuits can be constructed as an array of adder circuits. So this is one schematic way of doing each of these bits. This can get a little expensive as the size of operand grows. So the problem is like, yes, you can make a dedicated circuit on multiplications. Usually it's not necessarily a good idea. Okay, so what are the alternative? Okay, we need some background from you. Grade 3 math. So how I'm multiplying two numbers? Well, I don't really multiply and get the results out of the way. At least I'm not smart enough to do it. I'm not sure about you guys. So what I do is what I learned, in grade 3. So essentially, if I multiply 1, 2, 3 by 4, 5, 7, I do it one digit at a time. Yes, we can use calculators, but calculators is also going to do something. So we are actually building a calculator ourselves, right? So there's not shortcut here. So how are we going to do it? So if you look here, what we're doing is we're typically doing it one digit at the time in top input, and we multiply by the other output because we can easily handle sequential stuff, right? Because this is very sequential, right? I take one digit, multiply by that, get some, carries, and another multiplication, How you still remember it? I didn't put it in this prerequisite for the class, but I assume you remember that from high school. Anyway, jokes aside, then you're going to do the second digit, right? And you get the third digit, right? And the and, you just need to do addition. What is good about it? The good thing about it, we would take a complex problem, say multiply n bit number by another n bit number and convert it to a simpler problem. We multiply one digit here, right? Multiply by n, digit number, and then results are just added plus a little bit shifts, right? That's it. So you see that we go from a more complex problem to a simpler problem. Okay, so this is what really happens here. How about binary? Remember, our numbers are really binary. So how are we going to do this in binary? When in binary, it's not different really fundamentally. You take this bit, and if it's 1, we do multiplication. If it's 0, oh, amazing, there's nothing to do, right? 0 bits is amazing. Like multiplication on zeros gives just all zeros. And another 1, and addition. So this is how the same multiplication looks in binary format. Okay, seems like we simplify the problem, but how are we going to do that? Do we have any machinery to do this multiplication already? Any theories? Do we have anything? Do we have any logic already to do it? Like addition, we definitely have, but how are we going to do multiplications of 1 bit by an n bit number? Sam is right, we have shift, but before shift, what is at the core of this algorithm? When I do 1 by this and I get this result, so what do I do? It's not transfer. Krutik said, so several people said, Lian and Krutik said it's an AND, right? It's an AND, right? That's an AND logic. And we already have it, right? So essentially, calculation flow here is multiplied by 1 bit of a multiplier, add sum to sum and shift sum. So we need sum and shift, and both already exist. Remember, we already had all of that. We shift multiply by 1 bit and repeat the above. And multiply by 1 bit, this thing, it's an AND, right? As you guys already noticed. So you see sum we have, shift is basic operation we have, right? It's a logical operation. We have it as a part of logical unit, and an AND we already have. So we can build an multiplier out of the logic we already have. So it's cheap, right? And then essentially what we're going to build is that's the accumulator circuits. We had one register, another register was an output, right? We take register Y, shift left by 1, and register X, we take 1 bit, do an AND, go to an adder, and repeat the process. So this is a basic data flow for multiplication using the circuits, and it works, right? There's no functionality problem here. do you guys see any issue here? So it works, right? But do you feel like there is anything in this process that, if you like to optimize things, I'm a big fan of optimizations. Like all my research life, I spent things optimizing. Whenever something is not super optimized, that makes me unhappy. So what can be significantly optimized here? Like it works, by the way, there's no problem. And there, some multipliers were built originally like that. But can you do something better? So how we can make it more efficient? So it's like, what problem? Okay, here's this example for you to think in decimal first. So does it look like if we're going to multiply like that, based on this algorithm, something's going to be redundant? So I'll give you one example to provoke your thoughts on this. Yes, we don't like to multiply by 4 nines, right? We really want to multiply by adding in extra instructions with one subtract, but simplifying things afterwards. So multiply by 9, add to sum, shift, multiply by 9, add to shift, not a good idea, like a lot of operation. So if you're smart and look at the number, you think that's not the way I would multiply, right? So what I would do instead, I would take 999 and convert it into this format. 10K, so 10,000 minus 1, right? And then the multiplication would be like that. Why this is better? Because I like to multiply by this number. That's easy. Like, give me like any length numbers multiplied by 10,000. I'm very good at this multiplication, right? So that's not a difficult task. So neither is this. So even though it seems like I add some complexity, then I simplify things. In general, that's a very common principle that sometimes we do it in calculus all the time. We introduce some complexity at the beginning to make things easy afterwards. So it's the same thing here. So getting, this number from this number is just a basic shift. It's super cheap. As you can imagine, shifting numbers is really simple. And then you do the subtraction that we also have. No tedious multiplications and a lot of additions. So this is more efficient. So it's not it's a problem of corrections. Yeah, Sam is always one step ahead. Yeah, so we'll get to that, Sam, just a second. You're on the right track. So essentially, this was decimal, right? I would need to convert this into binary, right? How am I going to do this in the binary format? So essentially, there is a technique called Booth algorithm. When I'm going to share slides today, I'm going to put the slides on the examples on how to do the Booth algorithm to the end of the lecture. And as I said, if we're going to have time, we're going to cover that in more details in the tutorial. But the key idea, what I want you to remember, because at the end of the day, nobody is going to ever ask you in your job or even in research to build that from scratch. But I want to understand the key principle. The key principle is to take advantage of the fact that shift is cheaper than adding, whether the space is or in most architectures, and especially where space is at premium. So when multiplying by certain values, such as 99, it can be easier to think of this operation as a difference between two products. And we can do this in this format. But if you ask me, can this happen in binary? Oh, yes, and even more frequently, because in binary, the sequences of ones are even more frequent than all nines, right? You can quickly compute the probability of seeing this number versus seeing this number, right? So anyway, the thing is, when you had something like that in binary, you want to do this, right, instead of the original one, okay? So that's what we want to do. We're gonna look for a sequences of ones, right, and make sure we replace them with this. And that's what the Booth algorithm is gonna do for us. I know I might go a little bit fast. Any questions so far? So you get the basic principle. You see, like, we make it to work, then we try to make it faster, right? That's, in general, I highly advise you, or anything you're going to do in development of your code and your prototypes, always look for making the first quick prototype to work, which has the minimal functionality, right? Sometimes called extreme programming. It's very good. It's good in research. It's good in if you're developing something interesting for like big, like in, industry as well. It's a good strategy, because yes, you can do a tedious implementation of each feature, but then you might miss something and all that work is gone. So you really want to get a quick prototype first. So the quick prototype was what I showed you before, and the Booth algorithm is an optimization when you put some thought into it. Okay. Any questions? Good questions. How would circuit understand when to use shift instead of multiply? So that's what the Booth algorithm is going to cover. It's going to look for sequences of 1, and it's going to have a way to do things differently if you get these long sequences. Okay. So again, read the wiki page. I will share the slides. You can look at the slides in more details, and hopefully in tutorial I will have time to cover that. So I didn't give you the precise answer, Joan, for that. I just give you the high-level idea and the principle, what you can manipulate, which is looking for sequence of 1 and trying to avoid that. Okay. Wouldn't Booth algorithm add more overhead than it saves? The short answer, in most cases, no. It's actually useful. And as I said, when shift is cheaper than an add, and when the space is at premium, it is useful. And there is a reason, as you can imagine, people build the algorithm and implement it in hardware for a reason, right? So it is profitable. Okay. So some summary and reflections on multiplication. So the statement, again, which I inherited from previous people who taught this class, multiplication isn't a common operation as addition or subtraction, but occurs enough that its implementation is handled in the hardware. It is more or less true, although if you think about the recent trend on doing machine learning as they're one of the major, places we do computation, we do a lot of multiplications right now. So that's, people start to build dedicated circuits for matrix multiplication right now. Like there are multi-billion industry right now at Google, Amazon, Facebook, they all build circuits for that operation, like matrix multiplication, because it's used in machine learning heavily. So some of the things written in the slides, generically true, but maybe not true in the last 3-4 years. After a few years, maybe ML will go into some other route or will go out of fashion, and that might be completely true again. So this is why a lot of things in this, slides are relative. So anyway, so this is for you to know what's going on in the world. Most common multiplication and division operations are powers of 2. Which might or might not be true. Again, this is true for general purpose algorithms. It's not true, again, for ML, where they use multiplications of floating point numbers. So those are not powers of 2. But when there is a powers of 2, we had an amazing solutions to this. So we can do shifting instead of using multiplier circuits. And that's pretty much everywhere is better than multiplication, right? So if you need to multiply, by 4, it's just always better to shift by 2. The question to you, if you're going to do this right now in your code and start to replace all the multiplication by shifts, is it going to speed up your code or not? It's a tricky question. So Krutik said not. Yeah, so several people get to this. It's a compiler optimization. So the answer, if you're going to use compiler with a high level of optimizations, and if that 2 for power of 2 is provable, so compiler can prove that that parameter is always power of 2, then they're going to do optimizations. Because imagine you're going to read something from a file, right? And that happens to be 4, and you pass it as a parameter in this instruction. Compiler, there's no way is going to identify that that's this and replace this. So if you know that in certain places it might happen, you might want to do it. And usually, in a simple cases, the compiler will do it for you. So if you had a constant, then don't bother. The compiler will do it for you. But if you're going to use compiler with 0, and so the compilers can have parameters that you can place to compiles more optimal, but slower, or less optimal with few optimizations, but faster. So depending on which level of optimization, that optimizations might or might not happen, right? So that right? So you want to understand. So in general, it's a good idea. Like I get to use to program all the programming languages that not necessarily had good optimizers. subconsciously switch things by shift sometimes, but in many cases it's not needed, so that you know. But don't be surprised when you see that someone codes, right? Especially more senior people, because they think about optimizations a little bit more. Okay, another interesting part of logic is a thing called barrel shift unit. So the barrel shifter shifts and rotates the value D to the left by S bits. So essentially you have the input as 1 and 0 that tells you about how much you want to shift, right? And for example, if you had there 0 is 0, 1, it means that you just shift by 1. If you had 1, 1 and you want to shift essentially by 4, so you get that rotated value. So it allows you to rotate the value. This circuit is purely combinatorial circuit, unlike the shift registers in the labs. So this is just a contrast. Remember, this one doesn't depend on any other timing input. It's completely combinatorial, right? So this unit allows you to rotate the bits. Why? Can anyone think about which application would benefit from something like a barrel shift? Like what kind of manipulations does that? I faced this a couple of times in my experience in industry where this type of operations are very useful. So can you imagine something that each of us do all the time, including right now, like something that our computer is doing right now that needs a barrel shifter? Someone said mod. Yeah, like, I mean, mod is like, there is something like more massive than that. What is there? Something that not necessarily your CPU is doing, but maybe your graphics card is doing right now. Okay, so this is a pixel manipulation. Remember that the pixel manipulation, right? It has some standard format, either RGB or YCMK, like all these different formats. But essentially, they're very nicely pushed into the integer numbers, and the bits dedicated to each color is just a fractional bits. And very frequently you want to need one piece of the color, another piece of the color. So you want to do rotate or masking of it, right? So the barrel shifter might be good if you want to transfer colors. Okay, so this is the logic that we had. And essentially our view is right now is that we are sitting here, we had this fancy LU, we might have this barrel shifter, we had all the, inputs to control what's going on, right, out of it, and we had a maxis to select which of the units we want, right? There are also addressing logic. So eventually you see this thing gets complicated and we can get the picture through at the beginning, right? So, but we hopefully in this, lecture today, you learn a lot about how internals of their ILU operates, what we have in there, how we manipulate it. You're not going to be puzzled when you're going to see assembly language in a few lectures. You're not going to be surprised why there are several special opcodes, several instructions for something like -1 or +1. There is a reason for that, because we had a cheap implementations of those, right? And that happens by design. So, so circuit designers who build the chip, right? They try to expose something cheaper, and then people who are computer architect build something called instruction language or instruction. It's called ISA. So essentially within ISA, you represent those instructions in some intermediate language, and then you can run it with using something like assembly language, right? So you shouldn't be surprised by seeing some of the more exotic instructions. They do have a value, okay? Okay, so essentially what we did today, we covered a lot of the arithmetic compute units. So hopefully you get a very good understanding what is inside of it, right? And next time we're going to start and talk about storage. So storage for us, we're going to go all the levels. We're going to talk about SRAM, right? We're going to talk about registers. We're going to talk about other layers, such as the caches, memory, and how that's organized. Very briefly, because a lot of my research is on that part, on the storage and memory. So I'm probably going to show you some few additional slides to get you a little bit more excited and exposed about how, novel and new ideas comes on this part. And we're going to also learn about control logic. Okay, so one good question. A plus B takes one cycle, but how could A plus 1 be faster if it cannot take no cycle? So anyone want to take the question before I answer? It's a good question, by the way. I like it. Anyone is brave to take it? Please, guys, try. Okay, the number of operations is less. Well, we'd still do like kind of one operation. We might use less transistors, but that's a separate thing. Short of parallel, we're coming to something more interesting. Yeah, Aiden is close, right? Yeah, so essentially there are a couple of aspects. I think we touch on one, right? Shorter propagation delay, right? Whether that resolved in a shorter latency or no, the short answer, it depends. First of all, there is an assumption here that you make, sorry, I forgot the name, Juan, that add is always one cycle. I might disappoint you on the most advanced Intel chips and IBM chips, it can actually take multiple cycles. Why? Because the frequency is so freaking high that they cannot finish in a single cycle. So it might take a couple of cycles, but an increment might still finish faster, right? So sometimes you can win a cycle, and shorter propagation delay, you might also sometimes save on energy. So there are a couple of benefits. It's not trivial, but it creates an opportunity, and circuits people like increment is such a common operation, so we can dedicate some time of thinking of optimizing it, right? And it is there. Okay. Did we answer your question collectively? Yeah. Yeah, so it's an interesting optimization. So things are not like, I try to show things you from, first principle as easy as possible, like register is one cycle, everything, add is one cycle, but in reality, things are more complex than that. Okay. I think this is everything I have today. As I said, when we share the slides, everyone who is interested in the Booth algorithms, you're going to have the slides for that. And if you want to learn more, please learn. And then on Friday again, I will see how we're doing with questions and other materials. If I had time, I might go more into it. Okay. Please prepare for the quiz as usual. It will be on Friday. I'll get some nice questions for you prepared already. And yeah, that's everything I have. Anyone has any questions for today's lecture on the course in general? Are we going to cover how the mod operation is done? Not here, because mod is kind of more related to division, right? So we're not going to cover that. Okay. Okay, thanks a lot, guys, and my apologizes for the technical difficulties at the beginning. I really appreciate everyone who turns on your cameras. That really helped me at least to get a feeling that we had a live class, not that I talked to the black box. And I'll see you all on Friday. Thank you. I'm still here for a few more minutes if anyone has any questions. Thank you, guys.